All right, let's go ahead and get started. And so again, based off of feedback, I tried to post a live link. Oh, it's down at the bottom to the live note. So hopefully that's working. Let me know if it's not. And then, let's see, I feel like we have our paper topic selection coming soon. Is that right? Or week 3. So just make sure you get those turned in. And I probably need to help people with topics potentially. So just chat with me too during lab as well, what topic you're thinking about, or I can help research. All right, let's also give, so if you volunteered on Friday, if you could just stand up really quick, that'd be awesome. So big thank you to those of you that volunteered. Tori, you should stand up too, even though you're a student worker, you were still working. Yeah. So thank you guys, and I need to put in your extra credits still, so that's coming. And then if you didn't get to volunteer, don't worry, there'll be plenty more opportunities, so I need to get that on the calendar for you guys. But again, a big thank you, it was a big success, and again, more opportunities. All right, any questions or other things that we need to go over?
So is there going to be some sort of assignment where we put in the topic we picked for a paper?
Yeah, it should be on Blackboard. I think there's like a section where you can submit your ideas and then attach.
Like the one where it says like paper check-in?
Yeah, it's under the paper check-in assignment. But if you want to turn it in manually too, I will take a paper copy as well. Any other questions, comments before we dive into lecture? And so now we're kind of switching gears a little bit, right? So we were talking about bonding and how things come together. But now we're going to kind of switch, and this is a more like mathy chapter with kind of more formulas. And so now we're kind of back to basics of the ideal gas law. And so what's a gas? What do we know about a gas? So some of y'all tell me.
Composed of particles that are moving randomly and very fast in containers.
Yeah, so they're moving really fast. And then what else? So we make, we also make some assumptions, right, with our gases when we're talking about them in this chapter. And so what are our assumptions? And it goes into kinetic molecular theory. What does that mean? So definitely moving, right? But we also assume, so no interactions is kind of the key. And so, right, when we talk about just our ideal gas law and kinetic molecular theory, right, and you mentioned, okay, they are random particles moving around, but then for our purposes right now, we're assuming, no interactions, which obviously, breaks down pretty rapidly, just thinking about how things behave, right? So obviously things do interact. Let's just take liquid nitrogen, right? Well, liquid nitrogen can go from a gas all the way to a liquid, so that is telling you there's some sort of intermolecular force. But again, we're assuming not. And so with that, so we said, again, they're very far apart. So assuming no intermolecular interactions. And so like you mentioned, straight lines, right, until they collide with either one another or another particle. And so the other key term with this is that we assume elastic collisions. And so those are the two assumptions that we kind of make with this kinetic molecular theory. Is in addition to no interactions, we just assume that they perfectly collide and no energy is lost. And so again, right, that may not be true, because once things collide, then you start bringing in, right, their attractive forces. And so it's not going to be perfectly elastic, but we'll assume so. And so then we'll kind of get into the math then more on how these collisions, right, are related to pressure. So we see, right, molecular collisions are pressure. And so let's think about that more. And so we can think about, right, our barometer. We can think about, right, the pressure in our little eudometer tube with last week's lab, right? We were creating hydrogen, so then it's exerting some force. And so let's just define pressure. So pressure is just force exerted per area. So force, right, divided by area. And so, of course, right, if you have more surface area, then you're going to have less pressure. And then if you have, obviously, a smaller container, then less surface area, so more force. And so I would also think about, right, a balloon. So how does a balloon stay inflated? And so you have, right, the pressure of the atmosphere is beating down against your balloon. And so hopefully you inflated it then with enough air, right, so then it can have collisions and keep your balloon inflated against the atmospheric pressure. And so again, we'll break down the map of it, so we'll see, and this, right, is kind of makes sense, so it depends upon the number of particles. So we can probably think, okay, well, more gas, right, that's probably going to mean more pressure. Volume, so we'll look at volume. So again, that kind of goes back to our surface area and our pressure formula there. And then, so of course, we'll look at average speed, and then speed is also kind of related to, of course, temperature, right? So you start heating things up, they start moving faster. And so here's just a reminder of our assumptions that we're making. So again, with our kinetic theory of gases, we assume our collisions to be elastic, so that's both with any surface and with other molecules. So again, that means no exchange of energy. And then this is just reminding you that, right, an inelastic collision is when you do have an exchange. And you can often think of like a car crash too, right? So there's energy going into crumpling the car and all that. So that would be an inelastic collision. But again, we assume that they are perfectly elastic. And so then we'll start getting into, again, all these factors. So again, gas pressure is going to be dependent upon the concentration, which is related to our moles. So we can think back of our N. And of course, the greater the concentration, the greater the pressure. And so concentration is obviously related to number of gas particles. So we'll look at how to quantify that. And obviously, right, if we have more containers, or more moles in the same type of container, right, the one containing more moles has a higher pressure. And then so we'll look at how the volume affects it. So we'll look at this kind of more in detail, but we could, of course, imagine if we enlarge the container, well then if we have the same number of moles, so closed system, double the container, right, then that lowers our pressure. And so we can also kind of think about storms. And so how does this relate to atmospheric pressure? And so, right, variation in the pressure helps create winds and brings like storms. So we've been seeing a lot of rain and storms recently. And so if you have a high pressure region, right, that means a lot of airflow. And so that's usually associated with clear weather, so that high pressure usually clears out the storms. But then if you have like a low pressure region, that's usually means that you have some unstable weather, and then you might get a storm. And so all that, again, goes back to our how many gas particles, so like literally, right, how much wind do you have, either creating that high pressure, clearing things out, or again, right, you kind of end up with a vacuum, and then that'll bring storms to the region. And of course, right, this is also related to your ear. So your air is in, right, equilibrium with the atmosphere. And you probably notice this, like if you've flown, right? So then once the atmosphere changes, right? So if you have reduced external pressure, then that can cause your eardrum to then bulge outward, right? So then we have normal pressure on the inside, reduced air pressure, so then that causes that pain. And that's why they say, right, chew gum so you can renormalize that air pressure. So all those things are related. All right, so let's get into the math part, which I know everybody likes. And so let's first look at our units. So what units do we have? And so in lab, we mainly saw millimeters of mercury, and then torr is used pretty interchangeably. And so I'm not sure why this is, but they are the same, right? So 760 torr equals 760 millimeters of mercury. So those units can be used interchangeably. And then so looking at this little gas tube, and so this is where our measurements come in. So again, think about air is beating down on our pool of mercury here. And then this is, notice it's under vacuum, right? So if it's under vacuum, if we have, right, our air is hitting down on our mercury, so then it's going to drive some of that up, right, depending on how much pressure is beating down on this mercury. And so we find at 1 atm that the mercury column rises to 760 millimeters, or this 27.92 inches there, so depending how you measure it. And then we have other units as well. And so, right, we could have PSI, so that's pounds per square inch. So like your car tire, I think it's about 33 PSI. So just over 2 atmospheres roughly. Then you can have pascals or also kilopascals, which is not on here. So kilopascals would just be 100.325. These aren't used too often. Definitely we'll see a lot of torr though, and mercury. And then again, right, we saw inches of mercury, especially with the weather when we were looking for the barometer pressure. So American units are always given in inches of mercury typically. And then you might see bar. So a bar is again usually with like weather or any sort of atmospheric reporting. So they might give it in bars. And so 1.013 bars is an ATM. So this would be a good kind of cheat sheet. You might want some of these to help you convert. And they, just remember, right, atmosphere is our standard unit. All right, let's do a little conversion then. So we have a cyclist inflates her high-performance road bicycle to a pressure of 132 psi. And so see if you can convert that to millimeters of mercury. So go ahead and drive that, and then we'll probably have someone put it on the board. Does someone want to put it on the board? Go for it, Andrew. Thank you.
So I did kind of a two-step. So I started with, it was 132 PSI. One. And then first I converted that with the atmospheric pressure. And put the units of one atmospheric pressure equals 14.7 psi. So I put that in the denominator. Take out that unit. And then I need to convert atmospheric pressure to millimeters of mercury. So I can go from atmospheric pressure at 760 conversion. Too big, I won't give myself nothing. And I got about 6,100. 4, 5.
So that looks good. And then we'll just round because we only have 3 sig figs. So 6,820. And then, did everybody get this number? Okay, just double checking. The setup looked good. And you didn't have to break it down like that. You could have directly just made your conversion factor, right? That 760 millimeters of mercury is equal to 14 psi. But this is good too, right? If that helps you to just kind of break it down. Our ATM is, again, our standard unit, and it's 1, so that kind of helps. So that looks good there. Questions about this? All right, so now we'll start looking at our basic properties of gases. And so how it's kind of set up is we'll go through all of the little properties and how it kind of divides them into their main relationships. But then afterwards, we'll kind of look at the combined gas law and put it all together. And so looking at this, right, we have our 4 basic properties. So this is basically how can we describe a gas. So we have our pressure, and notice, right, it says ATM, so this is more for like combined gas law or ideal, which we'll get to what that exactly means. And so you don't necessarily have to be an ATM unless you're using one of these forms. And then same thing with volume, so we'll see we'll generally be in liters, but there are scenarios where it doesn't matter. Now this temperature one, where it says our temperature is in Kelvin, this is important. So it needs to always, 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 always be in Kelvin. And so why this is, we'll kind of go into, but basically it has to have some thermodynamic relevance. And since Kelvin goes from 0 on upward, as opposed to Celsius, that's negative, this makes more sense. So always, always, always be in Kelvin. That's the #1 mistake students make. And then we will quantify it in moles as well. So those are our properties. And so, of course, we'll start investigating how this happens. But basically, right, if we change one property, it has a potential to affect the others. And so we'll look at our simple gas laws to start off with to just describe our relationship with the pairs. And so blah, blah, blah. So we have these three plus Avogadro's. So now let's go into them in detail. So we start off with Boyle's law. And so basically, right, they were doing some experiments of Boyle and Hooke. They were playing with these little J tubes. And so they found an inverse relationship between volume and pressure. So let's look at this little schematic here. And so we have our piston. So we have a 1 kilogram weight exerting pressure on here. And so that gives us a volume of 1 liter and a pressure of 1 atm. And then they found, well, if we can compress that, so we'll exert some more force. And so that means it's going to shrink the volume by half. And so they noticed, right, if you shrink the volume by half, then the pressure goes up by that same factor. So now it increases by the factor of 2. And so we have this relationship. And so basically, right, it just states, so of course, if we decrease the volume, then it forces our molecules into a smaller space. And then what happens down here at the extremes? What comes into play? So what's kind of the issue? So that'll be a factor. And then just also like the physical space. So at some point, right, we can only compress so much. So the atoms, right, obviously they do occupy space. And then yes, we do, obviously if they get too close together, intermolecular forces come into play, so things can start to break down a little bit, at least, right, from our idealized scenario. And so the important part, though, is we're left with this relationship. So our P1 V1 equals P2 V2. So whatever our initial conditions are, we can solve for whatever one we need, either pressure or volume. And so this is a case where units don't matter. Right? So if you're just comparing a before and after scenario, your pressure could be in something else, in torr and pascals, PSI, it doesn't matter. Same thing, volume could be in milliliters, as long as it's consistent. So as long as the same. Right, so that just means, you know, they both have to be in PSI or they both have to be in milliliters, so that sort of thing. And so let's try, and then so the other kind of physical relevance that you can think about is diving, which just opens up a bunch of interesting discussions. And so they say for every 10 meters of depth, you add approximately 1 additional atmosphere of pressure. And so, right, you have to think about this, and this is why, you know, there's like training. And so if you're holding your breath and then, right, you rise too quickly to the surface, well then, right, you want to be exhaling, since of course your pressure would be decreasing by a factor of 3, so then your lungs obviously could expand to that. And so the other issue, so have any of you guys ever dived or anything by any chance? And so they often talk about like the bends, and so that is also from, right, again, you have a bunch of gases dissolved in your blood, so you also have like oxygen and nitrogen. So you also have to be careful, you know, when rising, that either you don't get sick from too much like nitrogen being released into your bloodstream. You also have to be careful that just like blood vessels don't burst or anything, so if you rise too quickly, you could have the potential to have like, you know, aneurysms and blood vessels bursting from those gases, you know, again, just coming out of solution essentially really quickly. So that's why it's important, and they always say like rise slowly and exhale, and I think you're supposed to do it in a certain amount of time. Which then my classes in the past started asking, like, what about those extreme divers that like hold their breath and dive to extreme measures? And so it does become a health issue for them. So some of them experience actually like aneurysms and, you know, health issues from doing that extreme diving. And I guess you have to train, and it's pretty crazy what it does. All right, let's try this practice problem. So as you breathe, you inhale by increasing your lung volume, right? So this is your diaphragm moves down and makes a greater lung volume space. And so if you have an initial lung volume of 2.75 liters, that's at 1.02 ATM. So let's just say, right, we could increase our lung volume to 3.25 liters, and we haven't inhaled any additional air yet. So what then is our theoretical pressure? Let's see if you can solve that. Trenton, you want to put it on the board? You look excited.
All right, so for the first ones, I got, what was it,
At 2.75 liters.
2.75 liters. Multiplied by the atmosphere, was it 1.02?
Yep.
Which then equivalent to what, 3.25 liters times a certain amount of atmospheres. So just like algebraically bring that over underneath. Liters cancel out, so I'm left with 2.75 times 1.02 atmospheres over 3.25. And then I think I got that. Got 0.863 atmospheres.
That sounds good. Is that what everybody else got?
Yep.
Excellent. And so that looks good. And it doesn't matter too much, right, who we set as P1 and P2, just as long as you keep, right, our one set of conditions together and then, right, our second set of conditions. So that looks good. And then in this case, right, they're both given in liters, but it didn't really matter for us just as long as the units match. Same thing, they just happened to give it to us in ATM, but it wouldn't have mattered if it was in torr or PSI. We could have still used this formula. Questions about this one? People a second to write things down. And definitely flag me if I'm moving too fast. That was one comment that I noticed as a recurring theme for a few people. And I know I talk fast and I move fast and I get excited, so just wave me down. All right, so let's keep looking at kind of our relationships here. And so now we have Charles's law, and so now we're just focusing on volume and temperature. And so now it says they have a direct relationship. Well, what does that mean? And so it says, right, the volume of a fixed gas at a constant pressure. And so that's the other thing that we should kind of emphasize when we're looking at these gas laws, at these like little pairs, right, is that we're holding, so right, holding, then pressure constant in this case, and of course also moles is constant. So it's not explicitly stated, but you kind of have to get that from the problem. And so they're saying, right, if we're holding our pressure constant, but we're going to increase our temperature, right, that means in order to have that same pressure, our volume is also going to have to increase to maintain that constant pressure. So that's all this is saying. And so it turns into this formula. So our volume and our temperature under one set of conditions is then equal to our volume over our temperature in our second set of conditions. And again, this is where it does matter that your temperature is in Kelvin. So you can't have negative number, you'll get really wonky stuff. So just highlight that, star that, whatever temperature has to be in Kelvin. And so again, right, our Charles's law states that our volume of our gas is proportional to the temperature. And again, it uses the term absolute temperature, so it has thermodynamic relevance, and we're setting our scale to 0 Kelvin, right? So 0 Kelvin, no motion, and obviously that'd be an extremely tiny volume of gas. And then, right, as we start increasing the temperature, so we think about what that does to our kinetic energy of those gas molecules, or start moving more and more. So if they have more energy, they're exerting more pressure. And so again, we need that greater volume to spread out those collisions so that, again, right, our pressure is unchanged. So that's what we're going for, is we're trying to have our constant pressure. And so this is Charles's law represented graphically. And again, right, we have these issues where we can only extrapolate theoretically since our gases start condensing into liquids. So there's our problem of reality. And so we'll watch a video for this one. And so, right, we have Charles's law. Again, so now we can think about this. And so maybe you've seen this. So, right, if you put a balloon, and I think I've used up a lot of liquid nitrogen, or else I would have gotten some more today. So, right, you can put a balloon in liquid nitrogen, and it'll kind of start shrinking, right? So that's just the same concept. So now you're decreasing the kinetic energy, so they stop moving around, and so your balloon kind of shrinks. You can do the same thing and heat up a balloon, or maybe, have you ever like washed out a milk container or something, and then if you cap it and let it dry, it kind of expands? You guys notice that ever? But it's the same sort of concept, right? So you have your hot water, you clean your milk jug out with it, but then you close it, so now it's sealed at that pressure.
Did something like that happen where I heard this loud pop in the kitchen? I walk in, I'm like, what happened? And I look on the table, and we had like those little plastic cups of like melons and pineapples and stuff, and it had been sitting there, and the gases from like the cut up melons and stuff had pushed out and popped out.
Yeah. That's pretty funny. All right, so let's kind of watch a more extreme. Where's the one that I like? It will do. I like this video.
Hi everybody, I'm meteorologist Jay Birschbach along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. And I just want to give you a sense for how strong, or how rugged these barrels are. Jay, if you could stabilize the barrel, I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day.
Sure.
That thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up.
Okay.
So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
All right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with. See, there's a good sort of jet of steam shooting out, and we're going to try to capture that by putting the plug back in. And we're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on.
Yeah, so that's super important, right? And of course, note how they sealed it up, so now they have the really hot gas trapped in there. And so now let's see what happens when we cool it down.
I'm going to spin it down. Rotisserie. Well, the first thing we should hear are a couple of ends of the drums popping in.
There we go.
A couple of the ends going in. There's the other end. There we go. Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside has cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is amazing. Looks like a pop can or a soda can.
Looks like a pop can.
So yeah, that's pretty cool. So that just shows you, right, the power of our atmospheric pressure. And then again, giving you a sense of, right, you cool things down, the kinetic energy decreases, and then obviously, right, our volume has to decrease. Yeah. So it's both, right? So right with that, so think about what happened, right? So we had they boiled their water, and so first we started with the open system. So they had, right, their flame and their water boiling. So right, they had all the gas vapor, really nice and excited, right? So from our Charles's law, right, that's increasing temperature. So now that increases our kinetic energy. But then once they sealed it, right, so once you seal it, we have the same number of molecules, but now from Charles's law, right, you cool it down, and so now if we want to keep that pressure constant, our volume has to decrease. But then you also have to think about, right, our atmospheric pressure is, of course, pounding down on it, so once this cools, it can go ahead and crush it.
What's the leading factor of it crushing vertically and not horizontally? Is it like just because there's more surface area in that direction? Or
It's just wherever it's weakest, it's going to be crushing in, yeah.
Does it matter that the temperature changed quickly? Or like if you just left it out and you were with it crush?
It would crush on its own probably, but like not as dramatically, I would assume. So right, cooling it down, that's going to condense it more. So if they had left it at room temperature, I would assume it might crush in a little bit.
Probably left out of the snow.
Yeah, if you left it out in the snow, it would still crunch down. So it just depends on that volume or the temperature difference, right? And so they were going for the extreme effect by heating it up. So they were trying to use the water vapor. And they used water, right, because they knew water has that extreme effect of condensing. And so they turned it into a gas, try to fill it all up, and then take advantage of water condensing back to a liquid. So it occupies even less space as opposed to like, right, nitrogen or oxygen where you'd have to cool it down more dramatically. And so you could play around with your balloon, yeah.
Little side question, but why is water like, we say like we can't compress it, like why is water behave like that?
Well, water, the only difference with water is that we just see our three phases, solid, liquid, gas, at like our normal, I would say, conditions, right? But, so the other one, so like nitrogen is not compressible once it's a liquid, right? So we say gases are compressible, so water as a gas is compressible. It's just that right away, those intermolecular forces take over. So that's kind of, right, the difference. So water has really strong intermolecular forces, and so its behavior is going to start deviating pretty quickly from our like ideal gas law, right? Because this is just talking about, we're talking about a perfect gas that we just compress and can make smaller, bigger. But right now, our kinetic molecular theory does not take into account intermolecular forces. So then we do have those perturbing factors. Does that make sense to people? So that's kind of the difference. But yeah, it's hard to keep it straight because obviously we know, well, you know, once they start getting closer together, there are intermolecular forces. And that is why they make a liquid or, you know, a solid. And so this chapter and the next chapter are also pretty related. All right, so let's try this problem then. So there might have to be some conversions. So we have a sample of gas, has a volume of 2.8 liters at some temperature. And then we submerge our sample into ice at 0 degrees Celsius. Its volume decreases. So what was the initial temperature? Do you want to put it on the board? We can also put on the far board over there. So I'm gonna put this one up, or are we still working on it? Well, let's look at this one together. No one seems as excited. So what formula do we need? How can we set it up? What do we start with?
I use Charles' law.
So Charles's law, so what's our formula?
V1 over T1 equals V2 over T2.
So that looks good. And then, so what were your first set of conditions?
I put 2.80 liters, and I converted the number to kelvins, so 2.80 liters divided by T1, and we didn't know that.
Good.
And then equals 2.57 liters, and then I converted this into kelvins, it's 273.15.
That looks good for the setup. So did everyone get this? And of course, right, don't forget your Kelvin. And so let's just hear, what'd you get for T1 then?
I got in kelvins 297.59 with rounding, and so converting that to Celsius would be 24.42.
And is that what other people got for this? I see some nods. Excellent. All right, excellent job on that one. All right, so one other comment that I got was that people want to break with the 2-hour lecture block, which I totally understand. It's a lot of math. So I figured we could take a little 5-10 minute break, maybe be back here at noon. But I did want to post, have you guys seen this FET website before? Yeah, so a lot of people have. I'll post a link for it, but it's a pretty fun, like, you know, demo to kind of play with these things if you never have. So I'll post a link, and so if you're bored during our break, maybe you could check that out. But otherwise, let's take a little break, and then so we'll start back at noon with the rest of our chapter.
Is it worth that 1%? You're like, okay, maybe if I wait long enough. That's all for fractions. Yeah, that's all for like converting. I technically did. It was just or maybe yeah. Was it automatic? Yeah, most of that stuff is just different. I assume I logically, but I didn't like. Obviously. This one?
And then she got a job back and figured that he doesn't like that.
Oh, is this how number for the amount of like actual particles there are? Finally, we use that. You feel the actual number of particles is like more important than stuff, but I guess it's fine. Trust us, dudes. I mean, that's like math. Trust this old site. There's a formula named after it. You can trust me. Try to fail. Trust. And then you figure out everything's wrong. That's like I've spent so long. We're telling you physics don't work. That's how they teach us. That's kind of how it works. Especially yeah. It's actually well, I didn't. It's cool when you get to see things go full circle. Like you finally actually understand.
We're all looking at your pencil, or your pen, I mean, your fountain pen. Yeah. Is Tyler sitting there? What?
Okay, here's the thing. I'm ready for the test. The test is fine. The only problem is I need to finish my entire week's worth of physics homework tonight after engineering club at 6.
Yeah, because I was trying
So.
to noodle or
It depends on how awake I am. Or I may just be half-asleep. I know the actual knowledge, however, will I remember it?
That's the best way to do tests, because then when you're looking over your notes, you're also surprised.
You're like, wait a second.
You remember this.
Your grade is a complete surprise. Oh god.
Gambling biology.
At least this is gambling test for all my entire life.
I don't know if you like gambling. Yeah. Almost like college career.
Oh, yeah.
One.
I did. So the first volume of breast temperature has to be equal to the next thing. So the volume from the beginning is what I have right here. And then the first temperature. And then actually
Okay, I'm invested.
Okay,
so if you're working.
Here's the thing, guys, I want to practice on this diet first.
Supposed to be.
Yeah.
15 was minimum.
That's fair.
Well, this is gonna stop and work.
And then when I finish
Nothing against you, but you have to go to court.
change that to Celsius. But really, it would just be minus 27.
I will try my best.
I don't know if that's somewhere or not.
Well, you did it as simple, you probably like, I forgot to do it. I was just doing really good. Like one time, you know,
So you need to work on everything.
Yeah.
If you're learning hard fixing,
Go back to the alphabet.
Because you can buy
I'm not really sure how they got.
So this one, did you get this set up?
Yeah, I got that set up.
Yeah, so then, let's just plug this in.
Or is it just like divide and multiply?
Yeah, so it's 2.8 times 273.15 divided by 2.57. So then that gives you the answer in Kelvin.
And you just convert it.
Yeah, so then minus 273 gives us the 24.
Thank you.
It's still embarrassing when you articulate yourself well. Especially. If there's any resources that use a lot, I'd like to know what it is. But I'm not.
All right, let's make our way back to our seats. So do we have any questions from our previous half of lecture? We feeling okay? All right. So let's look at, before I give you our kind of our trick here, let's look at our last relationship here. And so our last direct relationship is this Avogadro's law, so looking at moles and volume. And so again, right, we're assuming that temperature and pressure in this case are constant. And so this is kind of another one that probably should feel pretty self-explanatory. And so, right, volume is directly proportional to the number of gas molecules. So obviously, right, more gas molecules means we probably need a larger volume. Again, if we're holding our pressure constant, so our container is going to have to get bigger and bigger. And so this is one key part. And so equal volumes of gases contain equal numbers of molecules. So in reality, they do differ just a little bit, but again, we're making an assumption. We're doing ideal gas law, so everything is exactly the same. And so again, we can see this linear relationship. And so this is the formula that we need and care about. So our volume, our initial volume conditions over our initial moles is equal to our new volume and our new moles.
Can we simplify this in our brain to see like direct proportions are this equation where the first variable over second variable equals second first variable over second variable in their separate scenarios, and then for inverse you have that but multiplied by each other?
Yeah, so that's essentially where we're going. So I think that'll be more clear when we do our combined thing as well. But yeah, that's exactly it. And so again, right, our Avogadro's law states that it's directly proportional, hence why it ends up in that form as well, mathematically. And again, right, we can think about it. So obviously if we have more gas molecules, then obviously more of them are going to hit the wall, increasing that pressure. So again, our volume has to increase. All right, let's do another math problem. And so watch the wording on this one. So it says we have an athlete in this study, and they have a lung volume of 6.15 liters during a deep inhalation, and he has 0.254 moles of air. And then during exhalation, the volume decreased to 2.55 liters. And then now the question itself asks, how many moles of gas does he exhale? So you might have to do some subtraction. All right, so try that one. So you can ask your neighbor, your friend for help. Does someone want to put this one on the board? Or should we just walk through it together? As long as it's yourself. You can nominate yourself to put on the board. Wow, somebody seconded your nomination. Congratulations. Yeah, pressure's on.
Can I make this bigger? Can you all see this? I'm gonna assume yes.
Don't worry, I'll recopy it large. Moles. What did you get?
I'm gonna make this really big. Oh no, it looks like my writing. Well, excel. Sorry, I can't see your numbers. 1 4. Oh, there you go. I'm kidding. I see it. Okay.
All right, so that looks good. So first you have to solve for x, or n2. And so did everybody get 0.1? Is that 0.1053?
Yes.
So did everyone get that 0.1053? So this is moles, right, remaining in his lung. And so if you got to this step, right, that's a really good first step. And then, of course, it asks exhaled. So we had to do the subtraction, just like Camilla did on the board for us. And giving us 0.149 moles. And we'll say moles exhaled, just so we're clear. Questions about that one? All right, so now let's take a look at our, what I called our combined gas law. Actually, let's go into this next section and then we'll go back to the derivation. And so, right, we're given this ideal gas law. And so this will be important for some equations. But let's see how we can use this ideal gas law to also derive every relationship that we need. So we have our ideal gas law. So that says PV equals nRT. And well, now let's break down, well, what is all that? And so just like before, right, we had pressure. And so now this is our ideal gas law. So right, we said, well, pressure is in ATM, that's fine. Volume is in liters, N is in moles. And then this R is kind of where we're getting at. So R is our ideal gas law constant. And in your lab, you had a slightly more precise value. It doesn't matter too much which one you use, so you can use this more rounded one. And so let's look at a few things, actually. And so if you just Google gas constant, you would get a bunch of horrible, horrendous answers. And so you just want to know what gas law you need, so what constant you need based on your units. So later we'll look at other gas laws where we are going to be using this 8.314, so that's going to be if we're talking about joules, Kelvin, and moles. But that's not us right now. So right now we're in liters, ATM, Kelvin, moles, which corresponds to this one. So in Wikipedia it gives that super precise value. Again, we can just round it to 0.0821 for our purposes. So this is where it comes from, and again, right, there's so many different constants depending on what unit you're in. So that's where that comes from.
Say in the textbook, there's a little table with like 4 different R constants on page 434.
Yeah.
And it's got like different units. But we'll push on that.
Yeah, so that's the same. Yeah, so whatever page that is, that's just like a small, it only has a few of these depending on the unit. So this is just more extensive. So that's where that comes from.
Are those other constants used in different laws, or would it be used in this law if there were different units?
It could be both. So it could be used in this if we're in different units, or sometimes it's like a different formula where we're looking at like energy or something, and then we would plug in that. So yeah, we'll use, like I said, when we get into our more thermodynamics, we'll use the 8.3R. All right, so let's go back to how to derive, though, all these relationships. So this is really all you need to know, or at least the only formula you need for this chapter. And so why I say that, so let's start setting it up. So we could have some scenario, right? We have some conditions, our P1, V1 is equal to N1, R, T1. And then we could rearrange this equation to set it all equal to R, right? Because R is a constant. So now we get P1, V1 over N1, T1 is equal to R. And then we could say that this is true, right, for any other set of conditions. So R is equal to any P2, V2 over N2, T2. And so now we can just set these equal to each other if they're both equal to the same constant. And so now we end up with something like this. And so if you want to box this or star this, so this is another good form of formulas to have. And so, right, these are all the gas laws we just talked about. So Charles's, right, Avogadro's, all of them, I always forget their names. Right, we just rederive them through this relationship here. And so we can, right, we can get out our P1, V1 if we're holding moles and temperature constant. And so the trick is, right, you just cancel out the variable that doesn't change, or that are constant. And right, then we can rederive all our formulas. But then there are certain scenarios too where it's nice to have this combined form. And I'm not sure if we do them in this class, but I do have an example for y'all. And so you might see a problem. Let's try that again. You might see a problem like this. Let me make it bigger so you guys can actually see it. And so it says we have a gas at a volume of 800 milliliters at negative 23 degrees Celsius and 300 torr. So what would the volume be if we're at 227 Celsius and 600 torr? So notice, right, we're changing two variables. We're still holding moles constant. So holding, right, it never said that we changed our n, so we kind of have to read in our problem. But now for this one, that means that we can take this formula and then just cancel out the variable we don't need. So we don't need n, right? But now we can go ahead and solve for this using our new combined gas law formula. P1 V1 over T1 is equal to P2 V2 over T2. So go ahead and try that out to see if you can figure out what our new volume is. And so this would be one of the cases where we don't necessarily need to convert our volume and our pressure, but we do need to convert our temperature, so we can't leave it in Celsius. So I'm just going through kind of how to set it up. And so it was asking for volume. So all I did was rearrange our equation using the variables, right, to solve for volume. And then we just have to start plugging in our numbers. So our pressure was initially 300 torr, and I said it was fine if we left it in torr. Then times our V1, so that was 800. And then our T2, so that would be whatever, so 227 plus 273, so that should be 500 Kelvin roughly. So this we did have to convert. Then divided by T1, so that would be negative 23 plus 273. So that ends up being like 250 Kelvin times P2, so 600 torr. And we could have even had, right, 4 variables changing, or 3 variables changing, I mean, and solving for a fourth. And so what do people get for V2? And again, if we left it like this, then we should be solving our V2 in milliliters, since we didn't change units. So what do we get?
I got 799.76 milliliters.
So 799 milliliters, or about 800. I see. So that looks good. So that should be what you get for that one. Do we need to go over this in more detail, or people are okay?
I'm confused about the 500 Kelvin. I added 270. Wasn't the initial temperature there was 277 Celsius, and then we had 273, and that came out to be 550.
Oh, it's 227 though, for the T2.
Oh, that was fine. There we go.
Yeah. And so let's look at some other little tricks and hints. And Phoenix was kind of getting at it earlier, but I wanted to go over it again so everybody understood what he was talking about. And so let's just set up, right, this PV equals nRT again. And so other things we can notice, right, so if these two sides of the equation are equal to each other. So what do we say about pressure and volume again? What relationship did they have? So inverse, right? And so they're inversely related. And so kind of the trick is that any variables on the same side are going to end up being inversely related. And that makes sense, right? If this is being held constant, well, if one goes up, then the other has to go down. And so that means that we could say, like, moles and temperature would also be considered inversely related. Again, holding everything constant, right? If our moles go up, then our temperature has to go down to keep our pressure and volume constant. So that's what that's saying. And what that also means is, of course, if they're on the opposite sides, then they're directly related. And that's any two variables. So we could take, you know, pressure and moles. So if you're holding everything constant, right, as your pressure increases, then your moles is also increasing as well. So directly, right, we can say the same for volume and temperature, so those are all directly related. Volume and moles, right, those would be directly related. So anything on opposite sides, right, are directly related, so you could do that. What am I missing? So I didn't do pressure and temperature, so those would also be directly related. Does that make sense? And so again, right, this is kind of our key, and I'll just show, right, this formula again helps us rederive any of our relationships and all those laws we went over. Let's see, what do we have left? And so the rest of this chapter, so now let's get into our ideal gas law. And so this is used a lot in different word problems. Again, it depends what you're given. And so if you're not doing kind of like a before and after scenario, usually you need to invoke the ideal gas law. And so blah, blah, blah. So this just shows how to rederive our Boyles, Charles, and Avogadros like we saw. Let's do another practice problem then. And so now we're given, so calculate, and I'll just rewrite it. So PV equals nRT, with our n is 0.0821, right? Already forgot. And so now calculate the volume occupied by 0.845 moles of nitrogen gas at 1.37 ATM and our temperature of 315. And before I let you loose, this is just a reminder that now when we use this formula, we do have to be in ATM, liters, and Kelvin, right? Because it all goes back to that gas constant. So we want to make sure we're using the right units for this gas constant. All right, I'll let you work that out now.
I always feel a lot better when the units work out.
So I'll start writing it out at least. So I'll just rewrite our PV equals nRT. And again, we can tell we might need this because we don't have, an initial pressure and a final pressure. We're just given ATM, Kelvin, moles. Okay, well, I'm going to have to use this then. And so they gave it to us in the correct units as well, so that's kind of nice. So 0.845 moles or 8. And they already gave temperature in kelvins. That was, again, nice. So what do we get for our volume when we solved? So 15.9 liters. Is that what other people got? Excellent. And again, right, we know our volumes in liters since that's our standard unit for our gas constant. Excellent. And so now we get into these standard conditions. And so this is useful and often comes up to trick students in word problems. And so we have our standard conditions. And so this is just to try to make things easier to report. And so we call this STP. And so STP is 1 ATM, 273 Kelvin or 0 degrees Celsius. Then our standard amount is 1 mole. And our standard volume then, so you could do the derivation yourself, but this works out to 22.4 liters. So this is pretty key. And so again, you can see how they did this calculation. You can plug it in for yourself if you feel so inclined. But then the next part that's really important is, yeah, 22.4. And you might want to write that down somewhere because that's important. And so now we can say, well, that means that 1 mole of any gas, and again, this is for our ideal gas law. It will be a little variable in real life, but we say, hey, it's all the same at our STP. So that means, right, we have 1 mole of all of these gases, so helium, xenon, and methane. They would all be 22.4 liters at STP. And of course, that also means, right, 6.022 times 10 to the 23rd molecules of gas. And so the property that would be different is the density. So, right, we can say our densities will vary, though. And so density is just mass over volume. So obviously, right, volume is the same, but then their masses will be different. So that still matters. But
But you said there was actually like a tiny variable.
yeah, in actuality, like they would all be a little off. I don't have exact numbers, but yeah, they're not actually all this, but for our purposes, yes.
Mostly then.
Yes, it is close enough in real life, but yeah, for our ideal gas law. And so something that, let's do a problem. So let's do, so then how many liters is 8.575 times 10 to the 28th molecules? 8.575 times 10 to the 26. Let me rewrite this. Oh my gosh, I can't make a good 5, can I? Molecules of krypton at STP.
Can you take a look back at the standard conditions?
Is this,
Yeah, that. Okay, cool.
and so let's go over this, because again, you want to make the math easy on yourself. And so I would just go ahead and set up a proportion. So we can start off with what we know. So 8.575 times 10 to the 26. And you can write your proportion in a number of different ways. And I'm just going to use our relationship. Well, we said 6.022 times 10 to the 23rd. Well, that's equal to 1 mole, or 22.4 liters, right, since we're at STP, so we can take some little shortcuts here. And so something like this is the setup we're going for. Again, you could write your proportion in a different form. And then what do we get when we solve for x?
I got 31,891.08.
Is that what other people got? So let's,
31,891.084.
so let's see. So
31,896.
yeah, your 31,000 looks good. And let's see, we have 4 sig figs. So we could round that up to like 31,900 liters roughly. Any questions on this one? And so again, right, just set up so you can think of your conversion factors. So you have 22, and this is right at STP for gases. So 22.4 liters is 1 mole is equal to Avogadro's number. So whichever one is relevant. So that might be helpful. All right, let's see what else we have. So let's at least, we'll go through a little bit more of this, but probably pick up more partial pressure on Thursday. And so now looking at mixtures. And so, right, many gas samples are not pure, but rather mixtures. So even, right, obviously the air that we breathe. So here's our composition of air. So it's mainly nitrogen, so 78% nitrogen, and then only 21% oxygen, and then the rest, of course, other components of argon and carbon dioxide, so pretty small. And so, right, it depends on our application, and so our mixture can also be thought of as, of course, one gas, and that means, right, even though it's a mixture, our pressure, volume, and temperature can all be treated as one. And so we'll see how we can figure out our total moles from our pressure, volume, and temperature, and then figure out our different components. And so part of this also goes back to, again, right, they're not interacting. And so Dalton's law starts off with that the total pressure of a gas mixture is the sum of the partial pressures. And so this is a good hint. And so we don't know, right, our total pressure. Sometimes we can figure out our partial pressures and then add up everything. And so again, this is just a reminder that the particles, right, have negligible size, so we're not counting that. They don't interact, so we're not thinking about intermolecular forces. And so, right, we're assuming that, again, particles of different masses have the same average kinetic energy at a given temperature. And since our average kinetic energy is the same, then our total pressure is the same. And so the pressure of a single gas is called our partial pressure in our mixture. And then we can calculate our partial pressure because either it's related to the fraction. And so, right, we could do this for air, for example. So if we look at our air, we can just multiply it by our percent composition, and that relates to our partial pressure. Or we can relate it to our moles, and then you can figure out your pressure as well. Or maybe you have to figure out your mole fraction from your moles. And so we're left with this. So again, we have to sum all our partial pressures to equal our total pressure. And again, assuming our gases behave independently. So blah, blah, blah. And so this is also key, is our pressure is always related to our mole amount, so that is useful. And so it separates it down, so basically why we can do this, so of course we can calculate our partial pressure of each component, and it's related to our number of moles, which would also be additive as well. So then our sum of our partial pressures in our components always equals our total pressure. And so we'll stop at this thought, and so that gives us then for our mole fraction, so we can find our partial pressure of our component by multiplying it by the total pressure. And so again, let's just do this for nitrogen. And so we said that nitrogen is 78% composition of air, and we're assuming our air is at 1 atm, and so literally just multiply. So 0.78 times our 1 atm gives us 0.78 atm. All right, I'm going to stop there because I did want to talk about our lab and go over what we're doing today. So we'll revisit this. So I just wanted to give you a taste in case you're trying to attempt the homework. And you can, of course, bug me in lab. And blah, blah, blah. I'm just seeing what else we have to cover. All right, so now let's look at lab and talk about the theory. Because this is kind of important. But if we don't have any context, then we're not really going to understand what we're doing. And so our lab today is TLC, or thin layer chromatography. And so kind of why this is important. And so, right, let's just say you're a synthetic organic chemist, and so, right, you do your reaction, and usually when you do your reaction, even if it's relatively clean, there's still some horrible mixture or a side product. And so we'll say, so most organic reactions are messy. So, right, even if we have a really good yield, there might be side products or even starting materials that we need to separate it from. And so kind of the problem is, well, how do we separate compounds? So how do organic chemists separate compounds? And so one technique that they do 1,000,000 times a day would then be essentially a TLC or a column. And so they're related, this TLC and column chromatography. So let's talk about the theory behind both of these ideas. And so let's actually get a picture of what the heck a column is. So column chromatography is the actual application of the TLC. So the TLC is basically like a mini baby version of our chromatography. It gives us an idea of what compounds we have and how to separate them. And then if we were doing actual purification, we would put it in this column and separate our compound. So here's a good picture of kind of a column. Oh, where'd my picture go? Oh my gosh. So was that the only tiny picture? So here are more pictures of these columns. Oh my gosh. So here's another. So trying to give you the idea. So this is kind of showing your column over time, and the idea is you're separating it. And so now let's ask, well, how the heck do you separate it, and what is the TLC doing? And so, right, you have what's called this stationary phase. So that was basically all this kind of white stuff that you see in here. And so, right, the white stuff in our column, but also on our TLC plate, is called silica. And so this silica is really polar. And so it works to separate compounds by basically sticking or having the more polar things kind of stick to it. So your polar molecules tend to not move, so they tend to kind of stay on the baseline or move really slowly. And then your nonpolar compounds tend to move quite quickly. So of course, right, if they're nonpolar, they're not going to be attracted to the silica, and then they're flushed through with the mobile phase. So again, our TLC and the silica is our stationary phase. And then, so in lab today, what you'll be doing is you'll just be kind of testing and separating out some fruits and veggies, but same idea as a large column, and we'll have our mobile phase. So that's going to be our liquid, our solution, or eluent is the term chemists use. And so if you look at your lab, I'm trying to remember what your eluent is because it's a mixture. And so your eluent is this 70% acetone or hexane acetone. And so you're already given kind of the eluent. And so the thing with the eluent is that it's trying to get your nonpolar things to separate out from your polar things. And so this is kind of going down the rabbit hole, but right, if you were doing this in lab, in a research lab, or for new compounds, you may have to figure out what your eluent is. So in this case, right, it was just given to us, but usually it's some mixture of a nonpolar and a polar compound to try to get, you know, your nonpolar things moving, and then eventually get out your polar things.
What if your compound is only polar?
So if it depends how polar it is. So that gets into more like details of how to actually run the column and how to get a nice separation. And so, right, if it's super polar, it might get stuck down here, and that's where you might change your eluent to kind of what's called flush it out. So if you use acetone, methanol, that should move even extremely polar things. But you could, you know, get something that's really polar and it actually just gets stuck to the silica, and it depends what you're trying to do. So sometimes if you have like a really charged impurity, that's a good way to just filter it off. You could even use like a silica plug, it's called, and that would get off your like impolar, or excuse me, your polar crap. But it depends, you know, again, what you're doing and what you're trying to separate. But this is just kind of a preview to that. So again, that's what we're going to be doing today, is separating out our tomato compounds, so our lycopene and chlorophyll, carotene, right, all those. So kind of seeing them, kind of comparing the polarity, and then, you know, ideally you could run a column and actually isolate and separate these things out. So that's kind of what we're doing today. So in lab, we'll kind of go over the details of this technique, but this is really powerful and really important. So you want to practice, you know, getting your technique down today and just making sure you can make good spots and get good separation, because just having those basic skills would help you in an organic lab where you have to maybe separate a compound. And so to get into it even more, so have you guys heard of like those HPLC machines? I don't know if you would be familiar with that, but it's basically then a column chromatography except run by a computer, and fancy organic labs have other different, like now they make column machines as well where the computer can run your column. Of course, it's very expensive, but yeah, a working organic chemist would probably run at least a column a day, but maybe more. So super essential to separate. All right, so I think that's a good place to end. So again, we'll look at our TLCs and labs. Make sure you grab a lab paper, and then I will see half of you in lab today, and then I will see the rest of you on Thursday.